GM Volt or Malibu hybrids, they use these power split hybrids. Okay, so you need to understand this topic, unless otherwise, you don't really have full understanding of electrified powertrain. Okay, series and parallel hybrid is easy. Anybody can understand. Okay, we're gonna start with split hybrid configuration. So what does split hybrid configuration design space look like? The big picture. Okay, before we go into details. So that was this, and then we're gonna talk about start with a simple architecture or configuration, which is 1PG split hybrid, and then we're gonna cover 2PG split hybrids, and then we're gonna talk about compound lever analysis, and then after that we're gonna talk about multi-mode hybrids. Okay, so multi-mode hybrids uses clutches to transform powertrain from one architecture to another architecture. In other words, you can accommodate, you can use the powertrain as a, say, split hybrid or parallel hybrid or series hybrid. So you can put all of that into a single powertrain using clutches, because using clutch you can disconnect or connect shaft, power transfer. So we'll talk more about that later, but we're gonna start with single mode split hybrid. Okay. So why split hybrids are popular? Well, it started from disadvantages of series hybrid and parallel hybrids. And each series and parallel have pros and cons. So by sort of combining them two, if we can have advantages of those two, but remove disadvantages of those two, then that'll be the best, right? So split hybrid started to accommodate sort of advantages of both series and parallel hybrids, which is, for series hybrid, we can almost we can decouple engine operation from vehicle wheel, right? For series hybrid, but then both generator and motor has to be large if it was series hybrid, right? Because all the power has to go through this series path. But for say for parallel hybrid, we could use small one motor, but we need transmission to connect engine with the wheel, right? So we have somewhat limited engine operation. And if we can somehow combine them two and have the benefit of series and parallel hybrid, that's how it all started, okay? If you take a look at what's inside of the Toyota hybrid system, it looks something like this, okay? So here is the engine, and then here is the power split device, which is planetary gear set, and then there's motor here, and then generator on the left side. Okay, and this red part is the planetary gear set, and this planetary gear set is actually not that big. It's actually size of a cola can, right? And planetary gear set consists of three parts, three modules, which is ring gear, planetary gears, and then sun gear. And then there's a carrier that's holding planet gears, okay? And this was supposed to be video. Let me share this with you. Okay. Can you guys see? 플레이가 안 되네요. Anyway, let me just explain verbally. So what's happening here is, let me go back. So we have engine connected to carrier, and we have generator connected to sun, and then we have motor and the wheel connected to ring gear, which is ring gear. So motor and the wheel, and the engine, the carrier, and then generator to the sun gear. Okay. And once vehicle starts to move, the vehicle speed increases. And if assuming engine speed is, roughly the same, I mean, it increases, but if it stays the same, then your sun or generator speed has to be reduced. Okay. And that's because if we use this lever analogy, we can see that visually that assuming engine speed was held constant, if vehicle speed increases, then generator speed has to be reduced. And there's no unique architecture for split hybrid. Just like other architectures, we have many subsystems, sub-configurations, depending on how you connect your components with planetary gear sets. So, for example, if you look at these two examples, Toyota system have, again, like I said before, motor, large motor, and the wheel is connected to ring, and small motor, which is generator, connected to sun, carrier with engine. And that's what's shown here. But if you look at Chevy Volt, the first generation, then vehicle is connected to carrier, and motor is connected to sun, and engine and generator is connected to ring gear. So note that we have 4 components, right? Motor A, motor B, engine, and the vehicle. We have 4 shafts. And we are trying to connect that with one planetary gear set, which has 3 shafts: sun, carrier, and ring. And if you think about it, how many combinations do you think we can have in theory? We have 4 components, 3 shafts. Well, there's 24 combinations. So the Volt and Toyota is 2 out of those 24, okay? So if you enumerate and list all the combinations, then you have these 24 combinations, configurations. And this one is Prius, Toyota system. And this one is Voltec, the Volt architecture. But Prius is single mode, but Volt is multi-mode. Note that there is clutches. But there's no clutch for Toyota system, okay? So this was what I was talking about. So you have 4 components and 3 spaces, 3 shafts, okay? And you have 24 combinations. So you might wonder, you know, what about other 22 configurations? Maybe there is other good configurations, right? So this is the starting, the motivation behind our architectural study in our lab, okay? In our lab, we have been investigating a lot in the split hybrid architecture study, okay? And if you look at the entire design space, we talked about 1 planetary gear set, but what about if we consider 2 planetary gear sets or 3 planetary gear sets? Well, the combination increases exponentially. So, well, and that's because we have more combinations. We have more options to connect different things, right? So if we have 2 PG, then there are many ways to connect things, right? And then we have 4 components to connect with 2 PG, right? And by the way, I think I probably will talk more about that later, but there are 2 ways to use the second PG. Okay, so we just talked about 1 PG case, and if you look at this option, you can see that you always have to have 2 components on 1 shaft, right? So can you see? Because you have 4 components but 3 shafts, right? You have to have 2 components connected to 1 node, right? And when you have motor connected with vehicle, the wheel, then these are called input split. Okay. And when you have motor connected with engine, then these are called output split. Okay. So Toyota system is input split and Voltac is output split. Okay. And when you come here, so we just saw there are 24 configurations, but when you add one more planetary gear set, the number of configurations increases. But we have 2 categories here. So depending on how we use the second planetary gear. So we can use the second planetary gear as so if we connect 2 nodes, then we have 1 lever with 4 nodes, and then we can actually use the second PG as a speed reduction gear or speed multiplication gear. So maybe some of you may not be able to understand this, but because we really haven't dive into the lever analogy, but so using the lever analogy, if we ground 1 node, then this becomes simple step gear, fixed ratio gear, okay? Then we only have 1 degrees of freedom, meaning that this is determined by this speed, or this is determined by this speed, okay? But if we did not have that, then we have 2 degrees of freedom. We need 2 speed information to determine everything. And we need 2 connections, at least 2 connections, to be able to use as a split hybrid, okay? So either we can have 2 connections like this, or connect one with 1 PG, first PG, and then ground 1. So we can use the second planetary gear set 2 different ways, okay? And we grouped by that, depending on how we use the second PG, okay? And then we have total of, I don't know, 184, right? And if you use 3 PG, then you have more category and much more, many more configurations. So design space is humongous, okay? But this is not all. We have design variables. So we have planetary gear set gear ratio, right? Sun gear, ring gear, planet gear. So we have those gear ratios. If we have 1 PG, then we have PG and FD. If we have 2 PG, we have 3 design variables. If we have 3 PG, then we have 4. Okay. Oh, by the way, this is illustration representation of speed reduction gear. Okay. And you will understand better once we study lever analogy. Okay. But anyway, so this is just simple gain, you know, speed reduction or speed multiplication, or torque reduction or torque multiplication. Just simple here, okay? So we have 1 PG, we have 2 PG, we have and 3 PG. But for 2 PG case, I told you we have 2 categories, right? This category is either input split or output split with SRG, okay? But this one is called compound split configuration because we have 1, 2, 3, 4 nodes, and then we have 4 components. So each component is connected with each node, okay? And that's called a compound split. It's just some definitions, okay? Anyway, so we have this large, huge design space, and over the last, 7, 8 years, our lab has been exploring this design space, looking for the best new architecture. But this is impossible. This was impossible because the design space is so large that it was impossible to compute all the performance of all the designs. So this long, right? But we actually proposed one idea, and that was, how can we do this in a compact and tangible time, much faster? And I realized that in real world design space, it's usually drawn this way, or sometimes modeled in lever analogy. But if we actually combine everything and make the system modeling as compact as possible using compound lever or virtual lever, then we can actually reduce the design space much smaller. So we can run optimal control theory in this design space and then find a way to go back to the real design, then we can actually find the globally optimal new architecture in a very limited time. So this was usually this is the main concept of our architecture study, which we have been investigating for years, okay? And we had some nice results. Anyways, just giving you some idea of what we have been doing related to architecture study. But in this course, we're going to just focus on modeling. So the tools we can do this type of research, okay, which is modeling and optimization algorithms, okay. And we're gonna start with a simple architecture, which is one PG case, which is either input or output splits configurations. So we're gonna start with, let's start with a steady state model, okay? Again, we have 24 combinations, 12 input splits and 12 output splits. And here's the Prius and here's the Volt, okay? And we have 22 other configurations. So let's start with lever analogy. So when we first from system modeling and control engineer, usually we are given with this design, architecture. So then, which has 3D drawing, okay, or cross-sectional view. And we need to somehow, develop a model and understand what's going on. And one very nice tool we need is actually lever analogy, because that drawing is very difficult to model or understand. So, and the key part is the planetary gear set. So let's try to understand the planetary gear set. So this is kinematics of planetary gear set. Basically geometrical relationships, okay? So at point A, this is the relationship because you have speed with respect to the ring gear and with respect to the planet gear, okay? And then you have velocity of point B from planet gear perspective and from the sun gear perspective, okay? So this equation is just relating that this speed must be equal to this, okay? So this is from different perspective, from either ring or carrier or planet perspective. And same applies with point B. And if you combine these two, you can derive this equation. And by geometry, the ring radius must be equal to sun plus, this is P, this is S, this is ring, okay? So PR equals 2P plus S by the definition or geometry. Okay? And if you use that information, then this is what you get. And usually this is called, kinematic relationship of, planetary gear sets. And this is very important relationship, kinematic relationship. So this must be always true, okay, no matter what, because that's the geometry. So it's a constraint, sort of. And if you take derivative of that, then you can get this equation. But let's start with steady state analysis. So I don't know if, let's see. So if you look at this from, if you make this lever horizontal, then you can think of this as a seesaw, right? Where we have forces acting on it. And we have supporting force from the bottom, right? So this is a very, identical analysis, just static analysis, force balance, okay? But just looking at from the side, okay? So now, and the one main difference is that this is torque, not force, okay? And that's the key idea of lever analogy. So we are converting torque to force, okay? So we can visualize things much better, okay? Because torque is supposed to be rotational motion, but here, by drawing this lever and using this lever and put forces on it, which is actually torque, we can visualize a lot of things. So for example, this x-axis could represent speed. Okay. So for example, if you apply large torque here and torque here, then you will have the lever motion, right? And we're talking about dynamics here, and later on we will develop dynamic model, but let's start with simple steady state analysis. So steady state analysis means there is no dynamic motion, right? So now at steady state, this must be true, right? Because there is no motions, right? And we can get two equations out of it. One is that this static balance, and then another one could be the moment equation, meaning that for example, if you have force acting on this direction and then this direction, then what's going to happen? Or if you take moment about sun, then what's going to happen? This lever will rotate this direction, right? So there will be motion. So in order to make sure there's no motion, everything has to be balanced, right? So if there is this force or torque and this torque, then you must have this kind of torque to balance everything, right? To keep it steady. So this should be simple for ME background students. For EE, maybe you need to think a little bit about this later, okay? When you do some homework, okay? Anyway, so that's what's going on here. So this is an example of that. So we can actually derive, you know, ring gear torque, carrier torque, sun gear torque, and TF, which is the brake or road load external torque. And we can derive these equations, you know, speed and torque equations. But to do this, you need to use these equations. But later, you will find out there is actually easier way to derive these equations. Well, derive dynamic equation first, and then make all the dynamic components equal to 0. That's another way to derive, okay? And yeah, let's move on to dynamic model. We're gonna start with Prius first. So this should be a good exercise and example, okay? So before we do anything else, we need to start with a free body diagram. So if you're ME students, ME background, you should be familiar with this. If not, you need to get familiar with this, okay? You need to study. But it's not that difficult. It's quite easy to understand. So what it is you're decomposing all the components, you know, all the connections. Okay. So for example, we have so this is planetary gear, and this is engine. This is motor B. This is motor A and vehicle. And we are drawing a free body diagram with respect to planetary gear set. Okay. So planetary gear, this is how we draw a free body diagram of a PG, okay? So this is ring gear inertia. This is sun carrier and planet inertia. This is sun gear inertia. And then this represents the gear connections between ring and planet and sun, okay? And this force is the force acting on the gear, okay? We have action and reaction force, depending on how you look at it, from either from sun gear or planet gear, okay? And this force is that force, okay? Contact force at the gear, okay? And then this torque is force times Sun, number of Sun gear, and then this torque is force times ring gear, number of ring gear teeth or radius, and then for carrier, it's force times S plus R for the carrier. Okay? And then at this boundary, you also have action and reaction torque. Okay. So this is shaft. Okay. Imagine you cut the shaft. Okay. And then you have action and reaction torque. Whether you are looking at it from the engine perspective or the carrier perspective. And same applies here, action, reaction, right? So same magnitude, but different sign, different direction, okay? And if we assume no friction loss, small gear inertia, then we can drive it like this, okay? So let's start with engine side first, okay? So then it becomes like this, okay? So first, let's drive governing equation, okay? F equal ma or moment equals J alpha or torque equals J alpha, okay? So in this derivation, we're going to use this Euler equation. And this is exactly that, right? So for engine, inertia, engine acceleration, engine rotational speed acceleration, and then summation of torque, which is engine torque itself and clutch carrier torque, okay? And we need to drive the same equation for this side, which is carrier inertia, carrier speed equals to summation of all the torques. And there are two torques, which is TC, the action reaction torque, and the gear torque coming from the PG, okay? And if you combine these two, because if you think about it, omega E equals omega C, then we can drive this, right? Any questions so far? Any questions? Okay. Next, let's do the same thing for the ring gear or the vehicle side. Okay. So you just need to repeat the same process. Okay. Now we have one equation for the vehicle side, we have one equation for the ring gear side. Okay, so now it looks long, but basically inertia alpha, and then all the summation of torque, inertia alpha, summation of all the torque. It's just that there is this road load and motor torque and brake torque. There's more torque terms on the vehicle side. For the ring gear side, there's reaction torque and then torque coming through the gear, and that's it. And omega R, omega O are equal. And by combining those two, you get this equation, right? So it looks kind of long, but still one Euler equation. Output, this is motor A, and all the rest is sort of given by the model, okay? This will be input, right? Control input. Now, next move on to motor B, which is the sun side, and same procedure applies. So one equation for the motor B and one equation for the sun gear, and we can combine them too, and we have this equation. Okay. So, and then don't forget that we have this kinematic relationship for the planter gear set itself, right? Because planter gear set has this kinematic relationship that's built into it, right? This has to be always true. It's a constraint, right? So don't forget this constraint, okay? And if we list up all the equations we have 4 equations, okay? How many unknowns do we have? We have 4 equations. 윤태 학생, 제 정신이 확 들죠? 언노운이 어떤 게 있을까요? Just any thoughts, any idea, any comments? Anybody? 산민?
일단 오메가 값은 모르는 것 같습니다.
네. So we don't know omegas, right? Oh. Anything else?
F 모를 것 같습니다.
안 들리네요.
F 모를 것 같습니다.
네?
F요.
네. Yeah, we don't know F, right? Anything else? What about inputs? Input to the system. Control inputs. We can control engine, motor, torques. Right? Right? So if you have taken linear systems, automatic control, does this look familiar? You know? So we can rearrange this equation into a state space representation. Okay. And this is it. So we have 4 equations, and then we have many unknowns, but omega is actually state information, right? So rearranging that equation, we can come up with this state space representation. Okay, we have state vector, we have inertia matrix, and then we have input vector. But this doesn't look like, you know, x dot equals ax plus bu, right? This looks more like you know, ax dot equals b u. Right? So, but it's not a problem. We just need to inverse a matrix. So now it becomes that's the state space representation, right? But anyway, just so you know, if you want to solve this in ODE solver in Matlab, you need to inverse a matrix, right? So that it looks like state space representation. So that you can solve for x, you can solve for x dot, and then if you integrate this over time, then you get x. So now you can find these values. Okay. And this is output split example, okay? And the process is repeated. So you do the same thing for the vehicle side, and then I'm sorry, but engine side, and then vehicle side, and then motor A, and then the kinematics, and then you have 4 equations, and now you have governing equations. Oh, by the way, if you assume small gear inertia, so IS, IC, IR is very small compared to engine or motor or vehicle, right? Or you can lump them together. So this is lump inertia, okay? Anyway, so again, this was I1, which is Prius, and this was Volt model. If you look at the state space representation, you kind of can find some pattern, okay? So obviously this diagonal element is the inertia element, and rest is 0. And rest is 0, and then you have diagonal terms, and they are related to each speed shaft. And the last row is the kinematic constraint. Even though these two are different, but you kind of can see the pattern, right? And this is transpose of this, right? This is transpose of this, right? So this is a pattern we can find, right? Where omega is a vector, right? And there's also correlation between these. State vector, the input vector. And if we derive these models, all the equations for 24 configurations, this is what it looks like, okay? So if you look, you can see that this diagonal term is different, but they're the same for all of this, all of this row. But the vector is different for each design, each architecture. Can you guys see this pattern? So now we have all the models for 24 architectures. And now we can model and simulate these 24 architectures. But it takes a long time to drive these equations. Draw the free body diagram, drive 4 equations, and then put that into state space representation. This just takes a long time, right? Later on, we will also learn we can actually find this pattern and make this modeling process automated, okay? We can automatically generate these models, okay? And that can be very powerful tool for our system engineers, okay? And we can do lots of architecture study. we can program it automatically. Okay. Again, I mentioned earlier, but we can actually derive steady state model from this dynamic model. Okay, what is steady state model? Well, steady state means omega dot equals to 0, right? So if you put zeros in here, then this is what you get. And if you rearrange this equation, this is what you get, okay? And if you compare this with this, they must be the same. Here, this was derived based on, static balance equation, right? But we can also derive this from dynamic equations, okay? Okay, same applies for output split. And I think time is up. I guess this is perfect timing. So I covered lecture 14 within one lecture, right?